not if you like. Anyway, so, hello, good morning. How is everybody?
Yeah, good.
Good. So, we were talking last time about symbol tables. So we are, continuing on with that particular theme. We're going to use symbol tables as a motivation to discuss one of the sort of primary searching data structures, which is the binary search tree. But we've got a little bit left to go to get to there, so let's get through it. So, we did that slide. No. Okay. Come on. There we go. So we are sort of left with the question with symbol tables. Remember that a symbol table is basically a dictionary. However, one thing to note about symbol tables in this particular context, especially in a Java context, but in most contexts, in fact, keys are monotyped, right? The difference with a Python dictionary is that Python dictionaries can have many different types serving as keys in the same dictionary, whereas inside of the context we're currently talking about, the types themselves are monotyped, so that we can, there are certain operations which we know we can perform on them. For example, most types have the ability to compare values of that type against other values of that type. This is not necessarily true with respect to values in different data types. It is, for example, true that the way you order strings is by alphabetic ordering normally. However, it's not necessarily clear whether a particular string is greater or less than a particular float, right? So the fact that Python permits their dictionaries to not be monotyped means that they can't be as efficient as if they were going to, as if they did for reasons that we're going to examine. So, let's consider this issue of the orderedness of the symbol table. So, symbol tables can be more or less generic, as we well know. We can often improve algorithms by adding properties to data structures. Pardon me. Once again, we are going to talk about the introduction of an ordering to a data structure to be able to improve our performance characteristics. As with all instances where we add ordering as a property to the data structure, we do lose some generality, right? But we gain a lot of performance for that loss of generality. In the most basic version of symbol tables, we need only test for equality between keys. So, while it may not be obvious whether a string is, whether hello world is greater than or less than 7.3, you can certainly say that hello world is not equal to 7.3, right? So, one property that pretty much all data types, it's very rare you'll find a domain where equality is not defined. So, item lookup, if equality is all you have to rely on, becomes linear search. In principle, this is how Python does it, since keys of different data types may be combined into one dictionary. If inequality operators are defined for the key data, that is to say less than or greater than, we can construct what's called an ordered symbol table. This can introduce many useful operations and improve runtimes of existing ones. The price we pay is key monotyping. Pardon me. So, once again, once we have introduced the concept of ordering, we are stepping out of some degree of generality so that we might greatly improve our runtime. So once we have an ordered symbol table, a lot more functions become available, right? We not only, we still have our sort of delete and contains and is empty and size, but we also have a whole host of functions, such as what is the minimum key, what is the maximum key, what is the largest key less than or equal to the key that is indicated. Same thing with ceiling. This is a little bit interesting because normally we think of floor and ceiling as rounding functions on integers, right? But floor, technically speaking, the greatest element not greater than the thing you're flooring, right? And ceiling is the least element not less than the element that you're taking the ceiling of. If you're working with a restricted domain, like, just to draw an example. Ooh, chalk. There we go. Finally. If the keys in our symbol table are like 1, 7, and 13, right? Then the ceiling of 8 is a valid operation here. It doesn't return, or like even the ceiling of 8.7, right? It's still will pick this guy out, right? Does that make sense? Okay, good.
So what was the ceiling of 14 be?
Sorry, who said that? Say it a little louder.
What would the ceiling of 14 be?
What the, not defined.
Oh, okay.
In this case, it would return a null. There are no elements. There are no elements greater than the ceiling indicated. Make sense?
Yeah.
Question.
Who would ceiling is 7?
Yeah, I think so. Yeah, it's probably greater than or equal to. Yeah. Any other questions? Good. So, implementing a symbol table, an unordered symbol table, is reasonably simple. All we need is a data structure where we can combine structure, like we can combine a lot of different structures, by which I mean like in the C struct sense, right? We combine these into some kind of linearized data structure and we just perform linear search over them. So this is an example of using a linked list, a singly linked list, to implement a symbol table. You'll notice that each node in the list contains both a key and a value, right? So we add these guys sequentially, right? But we are not terribly concerned with the ordering, right? So what does that make insertion in this particular case? Complexity, yes? Constant, yes. So inserting into an unordered symbol table represented by a linked list, singly linked list, is a constant operation, right? So deletion, of course, this comes at the cost of search being a linear complexity operation, right? Good. One brief point to dwell on. When we are inserting a value into the list and that key is already in the list, that's an overwrite operation, right? Cool. So, I'm going to sort of gloss over some of the finer details of the binary search because y'all should know how binary search works because we covered it in 1MB3. So very roughly, if we have a symbol table which is sorted, right, if the keys can be expected to be in some particular order, this allows us to use the very powerful binary search algorithm to find a particular key existing in the symbol table, the same way that you would use binary search on, say, a list or a tuple in Python in 1MP3. So this is the binary search procedure. This is how binary search might be applied to an array. So binary search works, roughly speaking, by examining the middle element and comparing it to the element you're looking for. If the middle element is less than the element you're looking for, you know that nothing less than that can be the thing you're looking for either, so you can throw that half of the array away. And if the element you're looking for is greater, or if the element in the middle is greater than the element you're looking for, you know that it can't be higher than that, so you throw out the upper half of the array. This bisects the space of possible solutions by half each time, giving the binary search algorithm a logarithmic runtime. Make sense? Good, that should be review. Java implementation of the binary search. Binary search is I kind of already said this, it's a bisection method. As the size of the searchable section is divided by 2 at each step, our recurrence equation, and t at n is equal to t at n divided by 2 plus c, with c greater than 0 and t at 1 equaling 1. For simplicity, assume n is the power of 2. From the recursion tree, we have n at t at n equaling 1 plus c log 2n. Therefore, t at n is an element of big O log n. Binary search uses at most 1 plus log base 2n key comparisons to search the sorted array. So this is like, you know, we've talked about logarithmic inner loops, or shall we say, logarithmic outer loops on sorting algorithms, right? It's the linear inside bit that makes the sorting algorithm take a long time. Binary search is very, very, very fast because it really doesn't perform very many comparisons at all, especially if you take into account the thing that you're comparing it to remains constant the entire time, and therefore does not need to be refetched from memory. Make sense? Binary search? Good, good, good. Excellent. So, considering insertion for a moment, so if we consider maintaining an ordered array as the thing we're wanting to do, the insertion operation is actually still reasonably complicated, unfortunately. This is due to the fact that in order to insert into an array and maintain that array in continuous memory, it is necessary to shift every element past the element you're inserting down by 1 index, right? And possibly, consequently, expand the array's declared memory space by 1 if you're not using those rules from earlier on in the course about maintaining, like, trying to maintain at least a 50% overage in your memory declaration. So, this means that we have a log n operation followed up by a linear operation, so insertion on an ordered array is still linear. Yes. It's not linearithmic because we don't have to do the search each time we move one element, right? If you have a thing and then another thing, you take the maximum of those two in terms of big O, right? Good. Any questions about that? This stuff should be pretty good, right? Can I get a thumbs up? So what's the solution here? Rather than using an array, you probably want to use a linked list or some other similar data structure, right? In a linked list, what is insertion if you know the place you're inserting? What's the complexity? Say it louder. It's constant, yes. So if you're the same operation applied to a linked list would become wow. I know you know. I'm worried about the rest of these guys who have a test coming up. Yes. So we're performing the binary search, right, which is a logarithmic function. We are then performing the insertion operation on a linked list, which is a constant operation. So what's the big O?
Logarithmic.
Logarithmic. Thank you. So, good. So it goes. So, in summary, if we have an unordered array and we're applying binary search, or if we have an unordered array, we have to do sequential search, which is the textbook's name for linear search. This is best for very small symbols tables and slow for large ones. And of course, ordered arrays have the downside of a slow insertion operation, which can be ameliorated by using a linked list instead. However, it has optimal search and space for order-based operations. So, good. So let's talk about a different data structure entirely. The binary search tree. You guys are going to get quite a lot on binary search trees over the... question. How would you find the midpoint in binary search? Yeah, I suppose that would be linear, wouldn't it? Yeah, that would be a linear operation to find the midpoint of a even if you knew the size, it would be a linear operation to find the midpoint in a linked list. So, gross. Yeah, okay. Well, maybe there aren't so many advantages of a linked list over an array in that case anyway. So that's why clearly both of those solutions are suboptimal, right? So, let's talk about a more optimal solution, the binary search tree. So, binary search trees will remind you somewhat of the binary heap. However, we are not concerned with the binary search tree exhibiting completeness, right? We are allowed to have branches that end early, right? And we are also applying the binary search tree property, which is to say, we are now concerned about the relative orderedness of elements in the left and the right branch, right? So, roughly speaking, each key is larger than all the keys in its left branch and smaller than all the keys in its right branch. So, left branch you have smaller items, right? Right branch you have larger items. In contrast to binary heaps, binary search trees need not be complete binary trees. This does introduce some issues with respect to complexity, that we're going to spend topic 8 trying to fix, basically. So this is the anatomy of a binary search tree, right? So we might have some key at the start. All keys which are in the left branch of the tree are less than this key up here. Remember, Q, R, S, so R is less than S, so it's still there. And that holds at every level, right? All elements in the left branch of this E are less than E. All nodes in the right branch are greater than E. But because they're also in this branch to the left of S, you might say that all elements in this subtree are between E and S. Right? Make sense? Okay, so fine. This is fine. This is good. If we're using this to implement a symbol table, can you have duplicate keys in the BSD? What about in general? So, can you have duplicate keys in this thing if we're mapping a symbol table onto it? You're shaking your head. No. Why?
Because you only are doing like greater or less than, you can't, there's no position for something that's the same value as the key.
Mm-hmm. So in general, in symbol tables, duplicate keys are disallowed. Like think in Python, right? Does Python allow you to define a dictionary with duplicate keys? No, it'll just redirect you to the existing key if you try, right? Or if you think you're trying. So in a binary search tree which is being mapped onto a symbol table, we have a similar property where we don't have any duplicate keys that are existing inside of that symbol table, right? In general, though, certainly a binary search tree can be created which contains duplicate elements if we're not concerned about it mapping to a symbol table, right? Normally, the way that this goes is you make an arbitrary selection as to whether you place equal nodes in the left or the right branch, right? This is normally just for programming convenience. In the definition given here, it doesn't imply it one way or the other. But, you know, again, for programming convenience, typically you'll pick one. Make sense? Any questions so far? So, binary search tree nodes generally are composed of, at least if you're mapping it to a symbol table, we will have 4 fields. We'll have a key and a value field. In addition, left and right nodes. They're references to nodes, but you know, it is what it is. Additionally, we'll have an instance variable n that gives the node count in the subtree rooted at the node. This field facilitates the implementation of various ordered symbol tree operations. So we throw that in and come back to it later. But you can see that this is the way that the structure is done. This shouldn't come as too much of a surprise. This is basically this means that we are firmly in linked list territory, and we are no longer talking about things being equivalent to arrays, right? We are accessing the new nodes referentially rather than as some position inside of an array, right? The only reason that we got away with being able to do a tree inside of an array for binary heaps is because we're very firm about maintaining the orderedness, or maintaining the completeness property, right? Since we were maintaining completeness by construction, that meant that we could, do fun tricks like accessing parent and child nodes using formulas. If you want a more general structure which contains branches that may be of unequal length, then you're firmly in referential territory. Make sense? Good. So this does have a few corollaries. Certain operations which are fast for arrays are no longer available, like constant time lookup, right? This means that you can't just get to an element of the array. You have to actually walk, or you have to actually walk the data structure to access any particular element. Fortunately, this is a tree, so walking the tree is proportional to the height of the tree. Yes. And it's a binary tree, so in the best case scenario, that's log base 2n. Yes? No? Yeah. Cool. All right. With me so far? Question?
Is this like pseudocode or Java code? It looks like Java, right?
I believe this is Java. It's a Java snippet.
Okay, but it's like, it's all syntactically correct and whatnot.
It looks syntactically correct.
Okay.
I believe it is syntactically correct. I have not thrown it into a compiler yet. Someone's playing bowling on the ceiling. So, if we were to construct a skeleton for a binary syntax tree, which this certainly will be, compilable Java code if you take the comments out and put stuff in. Pardon me. In typical linked list fashion, we are defining the node and then using inside of the class containing the data structure, we have a reference to the root node. All other nodes will be accessible through the root, unless we want to keep track of some other things, but in this case we won't, so everything will be fine. Our major operations are put, get, delete, and an iterator, which we won't talk about too much. Primarily, we're interested in insertion and searching. So, search. Search should be already fairly straightforward for you guys to understand. It's very similar. In a lot of ways, it's similar to binary search on an array. You simply start with the root node, compare it to the element you're looking for, and follow the branch that it should be in based on the value in the node you're examining. Right? So in this particular example, we have this binary search tree. We're searching for h. H is, so S is greater than H, so we follow the less than tree. E is less than H, so we follow the greater than branch. R is greater than H, so we follow the less than branch, and then we win. Right? So, if the current node's key is greater than K, recurse on the left branch. If the current node's key is less than K, recurse on the right branch. If the current node's key is equal to K, return the value, or whatever value you're interested in. If this is a symbol table, you would be returning the value in the key value pair, right? If the branch you're recursing on is empty, then the search has failed. So this would be a Java implementation of your get or search function for binary search trees. You'll notice that we are not using recursion here. We are maintaining a variable of the node type and reassigning that variable with references to either the left or the right node, depending on how the comparison comes out, right? So this is not a recursive version of this algorithm, but you could very easily write one. Yes?
there be a difference in efficiency between recursion and iteration?
Would there be a difference in efficiency using this recursively versus non-recursively? Well, the recursive algorithm would blow up the stack, right? So the operating system overhead would be not great. Versus this, like, this is much, much easier than a function call, so this would be more efficient. In general, it's kind of like, recursion is kind of like the actual function call of, like, function call recursion in languages other than Haskell or other languages that, like, do that well natively, generally is avoided. So function call recursion in, like, iterative languages in general is like, you know, you do it if you're testing first years on how recursion works. Got it? So, like, it's still got a recursive structure, but we're doing it with loops, right? So, good. Algorithm outline, if key is equal to node.key, return the node's value. If key is less than node.key, recurse on the left subtree. If key is greater than node.key, recurse on the right subtree. Or I guess you could say iterate on the left and right subtree. Cost. Number of comparisons is equal to 1 plus the depth of the node. So, wherever this node is hiding inside of our data structure, that's the depth of that node is the runtime of this algorithm if you add 1. So here's an interesting question. How deep can these trees get? What's our worst case scenario?
It's as deep as there are elements.
It's as deep as there are elements, yes. So, somewhat similarly to, well, actually this might be the first time we're seeing, well, I might have talked about this. Yeah, I think I talked about this previously, but if you have a binary tree, which is just a general binary tree, the worst case scenario for this guy is basically a linked list, right? It depends on the order in which you add the elements, right? And we're going to see this during the insertion operation. But essentially, if you say, I'm adding 5, I want to add 4 to this. I make a branch here, add the 4. I want to add 3. Okay, I go down here, go down there. There's a 3. Add 2, go here, go here, go here, make this branch. Add 1, go here, 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 here. Right? Binary. This is still a binary search tree, but it is a binary search tree that is deeply suboptimal. Right? Again, this is not a problem that we're going to solve until topic 8. All right? But, you know, just keep in mind that in the worst case scenario, the number of the depth of the node that, so that's the worst case scenario binary tree. The worst case scenario search on the worst case scenario binary tree is the item you're looking for is right at the end of that, right? So that means that you have to go through every single node to get there, which makes this no better than linear search, right? That being said, in the average case, it's not going to be that bad, right? So we're kind of, once again, in quicksort territory, where if you perfectly construct the worst case scenario, your runtime just falls off a cliff. But if, on average, it's a lot better than that. Question? It depends on how you're numbering depth, right? So if you consider the root node to be at depth 0, then there you go, right? Any other questions? Good. So let's talk about insertion. So in order to insert a new node into a binary search tree, we are always going to be adding a new node at the end of a branch. We're not doing anything funny by adding nodes in the middle of the tree. Not yet, anyway. So, that's a preview of things to come. So, if we had a structure like this, right, and we were trying to add G, we perform our comparisons, tracing things down the tree, and then, once we hit a null, right, once we hit a null branch, we create the new node, put it on the null branch, and thus we have performed insertion, right? So again, in the worst case scenario, this will, you can construct a linear data structure out of this, but, basically you have to have ordered data and then add that to insert every element into a binary tree in the order of the already ordered data. So one way you could think of to sort of defeat this problem is the same approach that the sort of thing we kind of did with quicksort, which is you can randomize the data and then construct the tree out of it. That's one way of avoiding this problem, the same way we avoided the problem in quicksort. Make sense? Be that as it may. Rather than an empty branch indicating failure, this is where we insert the new node. The structure of a BST is dependent on the order of the items added, on the order in which the items are added, I should say. The best case scenario is a complete binary tree, which is unlikely to happen naturally. So in the same way that the worst case scenario is unlikely to happen naturally, the best case scenario is also unlikely to happen naturally. So, our BST put or insert operation associates a key with a value. So we search, so to take the insertion procedure and generalize it to put, remember that put will overwrite a value if it finds it. So basically you perform the search operation, and if you find the key, then you overwrite, and if you don't find the key, then you insert. And that generalizes us to the put procedure. Make sense? So put is the combination of the the search stuff and the insert stuff. Make sense? Any questions? The stuff isn't too bad, right? Yeah. Just wait till we get to red black trees. Question?
Can you explain the resetting links on the way up?
Resetting links. Let me see, where does it say that?
In the bottom right picture, the last step.
Yeah, right here. I have no idea what they're talking about. We have not set links, so why would we need to reset them? That doesn't, I don't know what, I don't. Maybe there's like something in the textbook that never made it into the slides. All of these diagrams are out of the textbook, right? So I'll take a look at it and I'll see what we've got going on there, but good point. Good. So, minimum and maximum operations. Min and max are pretty easy on a binary search tree. For minimum, you just always follow the right branch until you hit a null, and that's the minimum. For maximum, you always follow the left, or sorry, I said right, I meant left. You always follow the left branch until you hit null, that's your minimum, that's the minimum procedure. Always follow the right branch until you hit a null, that's your maximum procedure. Fairly simple, right? Floor is the largest key in the BST, less than or equal to the key we are flooring. Ceiling is the smallest key in the BST, greater than or equal to the key we are ceilinging. So, taking the floor of G, right? we take a look at S, right? We travel down. E is less than G. And so, you know, this R is greater than G though, so this will be the floor, right? So you hit a child node, which is greater than the thing you're looking for, so you keep the parent of that child, and that's your floor. And then ceiling will be the exact opposite operation, right? So you go, so you're looking for Q, right? So that's less than S, greater than E, less than R, right? And then, yeah, or sorry, QRS. No, R is less than Q, so you keep that because this is still less than, right? Yes?
Is it not possible for the H to be like an F? In which case it would end early at the E.
Is it possible? No, H must be greater than E.
Yeah, so if it was an F, when they go E, F, and then it would end early at the E.
No, but if it was F, then, okay, so G, E, F. All right, let's do this. All right. So we've got, so the thing we're trying to, this is floor G, right? So E, and then R, and F is the scenario, right?
Yep.
So G compared to E, E is less than G, so we look down this way, right? R is greater than G, so, and F, yeah. Do we have code for this? I don't know. I don't think these are particular, all right. Here we go. So finding floor, G is less than S, so floor G must be on the left. G is greater than E, so floor G could be on the right. Floor G in the left subtree is null, so this is the result. Okay, so it is falling down the branch until it hits a null. Okay, all right. It does trace the complete tree. All right, I apologize for that. Okay, anyway, at any rate, so deletion then. Deletion is kind of a pain in the butt on BSTs because in order to delete a node, you have to like restructure the tree and like hypothetically swap some lower node, some child node into the parent position. So that's gross and messy, and nobody wants to do it because, you know, if the child already has 2 children of its own, that means that you would end up with a node up here with 3 children, which of course violates the binariness of the binary search tree. So, one way that you can approach this problem is to, quote unquote, leave a tombstone. So, if deletion means taking a key and setting its value to null, if we remember, a null value, nulls are disallowed as values, right? Proper values anyways. So a null could be used to indicate that a node has been deleted. This node would then still guide the binary search, right? You don't have to restructure the tree. But this is an unsatisfactory solution because they occupy memory. Basically, this means that your binary search tree would only ever grow, right? Which is not necessarily an optimal solution. Make sense? It would work though for a period of time. Yes.
Then, if you had that there, what would happen when you're doing insert? Because if insert requires you to find null, and then you insert after the null, then what? That's not what.
So you have to check to see if it has children too. If you're looking for a null child, not a null value.
Right.
Yeah. Any other questions? Cool. Let's see. So the alternative to this is actual tree manipulation. We have a procedure known as Hibbard deletion. So to delete a node with key k, we search for a node t which contains it, and delete t by setting its parent related to null. Right? So to delete c here, we replace this link with a null link, and this becomes available for garbage collection. We then update counts after the recursive call. Of course, if it has children of its own, right, we don't just delete the thing. We set this. We set its one child. E will now point to the one child that it has, freeing R for garbage collection. Update counts. And then, of course, with two children, it's a little bit more tricky. This is the harder procedure that we tried to avoid by doing the lazy way of doing it. So, T is replaced by X, which is the minimum key in its right subtree. X's right child is X's replacement. So X dot left is equal to T dot left. X dot right is equal to T dot right. If T is right, then X right is null. So to speak, if we're deleting E, right, the first thing we do is we pull R's rightmost child up into E's position, right? Then, is this going this way? Look, yeah, it's okay, all right. So, we find the thing we want to delete. We go down the greater path, then the less path. We pull this guy up into this position, right? And then pull that, make that into the child node of the node of the parent that the node we're deleting was using. Does that make sense? To some extent? Okay. Well, thank you very much, everybody. Have a good weekend.